Hello, so thank you for coming to my talk. My name is Tomáš Glozar. I work for Red Hat as a kernel developer. I work on tracing real-time latencies. And today I will be telling you how I got to maintaining Linux on Itanium. So what is Itanium? Itanium is a 64-bit architecture that was developed at the end of the 1990s together by HP and Intel. It was supposed to succeed HP's PA RISC architecture, which was one of the oldest RISC architectures from 1986, and it was getting quite old, so HP decided to replace it. And they decided to collaborate together with Intel to create this new architecture that they originally called PA-WideWord, then Intel renamed it to Itanium. And it was supported from 2001 to 2021. That was until fairly recently. And it is based on a typical VLIW, very long instruction word design that Intel decided to market as explicitly parallel instruction computer, or EPIC. And Intel's idea was that this would replace DEC Alpha, HP PA RISC, and also SGI MIPS Unix workstations and servers. And Intel also wanted it to eventually replace its own aging x86 architecture. And this is an HP ZX 2000 workstation, which was one of the first workstations that was created with this architecture. But there were also other machines. For example, this SGI Altix 450 server was powering the information system of Muni for some time. This is a bigger machine. It was used to run an Oracle database on Linux. So how did Linux get to Itanium? Itanium was supposed to be a really big thing, and Intel wanted everyone to port their operating systems to it, including AIX, HPUX, and OpenVMS. And they also decided to involve the Linux community. And this was called Project Trillion, and Intel was contributing to the Linux kernel directly to support Itanium when it would eventually launch. To give you some historical context, this followed IBM's announcement to focus on Linux. This was in September 1998. And Linux already supported several architectures at this point, from x86 through SPARC, ARM MIPS, Motorola 68K, DEC Alpha to IBM S390. But all of those predated Linux. Linux was created in the 1990s. Those are all architectures that were older than Linux, including DEC Alpha, which is the youngest of these, I think, maybe together with SPARC. But neither of those were ported directly by the company that created the architecture. They were ported by the Linux community. Unlike those, Itanium support was planned before the release of the architecture, and the major contributions to it were made by HP and Intel themselves, which is the same thing that later happened for other architectures like RISC-V and LUNGARCH most recently. And as I said, HPUX, AIX, also Windows and OpenVMS were also ported to Itanium with assistance from Intel. So this is how we got to Linux on Itanium. Of course, Project Trillion didn't only include the Linux kernel, it included also glibc and binutils and the GCC. But the problem with Itanium was that first it was delivered 2 years late. That was one problem, because it was supposed to be this new thing that is going to revolutionize everything according to Intel, but for a long time Intel was just talking about it and didn't actually ship anything. And the other much bigger problem was that when Intel eventually shipped something, which was the first Itanium CPU, which was codenamed Merced, its performance was abysmal, and it was dubbed Titanic after the Titanic ship. And as you see, this is a snippet from news from the time. This was published on OS News. They called it a massively complex and hideously expensive beast of a CPU. And this is not very good for publicity, but Intel decided to try to fix this fiasco with Itanium 2, codenamed McKinley, which was its successor. And Itanium 2, fortunately, was good enough to keep Itanium in the game. It was a CPU you could use. If you look at some results from LinPack benchmarks on parallel computation performance, it is about the same as the contemporary PowerPC G5, so it doesn't have a bad performance, at least in those parallel tasks, but it was not nearly enough to revolutionize everything like Intel thought. And this led to poor sales of Itanium, also because the performance highly depends on a compiler. So here I show you a bit of a more modern benchmark. This is with Llama 2.c, which is an LLM inference model. And I ran this on my own dual-core 1.6 gigahertz Itanium 2 with different compilers. And you see that if you use just bare GCC, you get about 18 tokens per second. But if you use Open64, which is a faster optimized compiler for Itanium, you get more than double the speed. You get even more speed when you use the GoToBlast2 kernel for vector matrix multiplication, which is written in Itanium assembly. And you get even more speed with a new HPC compiler. And this is because to compute the vector matrix multiplication, which is the main thing that you need to do for this Llama 2.c LLM inference, you have to utilize the 2 FPUs, and you also have to utilize the parallel instructions that can multiply and add 2 32-bit floating point values at once, and the compilers simply cannot schedule the instructions properly, and most of the CPU gets unused, and the performance is slow. Of course, this does not compare to modern CPUs. For example, my Intel Core Ultra 7 mobile CPU has much higher performance. And efficient open source compilers were not immediately available from the start, which is a problem because people wanted to use the computers, but they didn't have enough toolchain support to make it a better choice than something else. And because of this, the Itanium sales forecasts didn't meet any expectations. You can see that Intel has progressively updated their expectations. Initially, they thought it will reach $40 billion in sales by 2002. In the end, it didn't even reach $5 billion by 2006. And because of this, Intel decided to discontinue the architecture. So by 2021, Intel stopped the production of the Itanium CPUs. Now you might be asking the question why it took so long. It was because Intel had contracts with Oracle and with HP to produce those machines, and people were running their software on it because they were persuaded by Intel to buy it. But the last HP Itanium server will have the end of life at the end of 2025, which is this year. So this is the last Itanium machine, which is called HP Integrity RX 28000 i6. And because of this end of life, Itanium was orphaned in the Linux kernel. This was announced in 2021, and by coincidence, this was the same time when I decided to buy an Itanium machine. This was completely unrelated to Linux. This was in COVID, and I was looking into OpenVMS. And to get an OpenVMS machine, OpenVMS was not ported to x86 yet at that point. It only ran on alphas and on Itaniums, and alphas were too expensive at the moment because for the historic value of DEC, retro computing and stuff. But I managed to buy an Itanium server in 2021. And when I got it, I wanted to run all kinds of things on it, obviously. So I started looking into how I could run Linux on the machine. So there were 2 officially supported up-to-date distributions in 2021. Those were Debian ports and Gentoo. But neither of them booted on my machine. They started giving various different error messages. And based on this, I assumed that the Linux kernel support is just broken, and there is no way of successfully installing them. So I went back and I was stuck on RHEL 5.11 and Debian 7.11, which were stable releases back from 2010 and earlier that supported Itanium back then. And they were running on an older kernel, which worked. And I had some fun because RHEL has Xen support, and in Xen under Itanium you can also install Windows. But I gave up on the latest Linux kernel, at least for the time. And I was totally unaware that the Linux kernel deprecated Itanium. I thought it's just a bit broken, but it's still supported. Maybe you can compile it in a way that works. Maybe I can get it running, but I was a bit skeptical. But I was playing with Xen, and I managed to install a beta version of Windows Longhorn for Itanium, which is it is actually the only version of Windows where you have the Luna theme on Itanium, because they removed that for the production release, and you can run that in a VM. You can also run it on bare metal, but it's a buggy beta build of Longhorn, and it's a bit of a pain to run it on bare metal. So the Xen VM worked quite well. But back to Linux. I was also involved at this point in T2 Linux. T2 Linux is a source-based Linux distribution that has this good feature. It can build fully working installation ISOs for many architectures via cross-compilation. Maybe if you know build-root, it's something like build-root, but with more software support. And I talked to the T2 guys and offered my machine for testing. And they tweaked some Itanium configuration files related to the toolchain. And they have managed to build an ISO for Itanium. But there was an error in the kernel configuration, and the T2 built-in kernel was not able to load any kernel modules. So I did not have any drivers. But I made a mistake, and I did not notice at all that there is this error in the kernel configuration, which was, again, specific to T2 Linux. It was not a bug in the kernel source itself. So I went back and I built a statically linked 5.15 kernel that worked for me, and I continued using that. So I continued to believe that the latest upstream kernel is broken on Itanium. Then, in 2023, my friends with whom I have been talking to in the T2 Linux community told me, hey, Tomáš, Itanium is going to be removed from the Linux kernel because it's apparently orphaned. And I told them, well, it doesn't work anyway. Why bother maintaining it, right? But then one person came to me and said, the kernel always worked for me. What do you mean broken? I don't understand that. So I tried the kernel, and I found out that it actually works when you configure it properly. So I went to the mailing list, and I suggested that if the decision to remove Itanium from the kernel is ever reversed, I will volunteer to maintain the architecture. But my hopes were not that high, because the decision was already made, and it seemed that everyone wanted to just remove it and remove it from everywhere, because it was something historical and not relevant anymore. But to the surprise of myself and also my friends, we got a reply from Linus, and Linus said that he is not exactly for removing it, and that he is mostly concerned if it's maintainable, and that if we can maintain it out of 3 for a year, then he can try to reintroduce it to the Linux kernel again. So there has been some comments on LWN. There was this article called "The Push to Save Itanium," and someone said that it's not realistic for a few people to maintain an architecture out of 3, and that we probably don't want to pay anyone to maintain that for us, and it's just impossible. And well, let's see how impossible this is. Now, so the question is whether it is harder to maintain Itanium or to do a live demo. Yeah, this is the right size. Okay, so this is my RX 2620 HP server. This is currently in the EFI boot manager. And this is a grab menu. And oh, this is the wrong thing. Yeah, and you can see there are quite a few kernels here that are definitely more recent than the removal. 6.17 was released, I think, last month. So let's see if it boots. It takes a while to find the drives. Yeah, we have Btrfs. Okay, so the system booted, it works. It's apparently not that impossible at all. So now the question, of course, is how did we achieve this? And for that, I will go back to my presentation. I created a GitHub organization called Linux IA64, and this is run by me and my friend Johnny Mnemonic, and also with contributions from others. And we have 4 repositories. One is a fork of the Linux kernel, one is a fork of glibc, one is a fork of the SCI Itanium emulator. I will get later to that. And we also have CI for testing stable releases of the Linux kernel, because the stable releases, they pull patches from mainline. And for example, when Linux 6.17 is released, then until 6.18 is released, the fixes are also put into the stable branch. And there are a lot of stable releases, so it's good to have a CI that can automatically test that those boot on Itanium. And the current status is that the Linux kernel is at 6.17, as I showed you, and 6.18 release is in development. I have to update some IRQ-related code that got changed upstream, but it won't be very difficult, I think. And glibc, which also removed Itanium in the meanwhile, is at 2.42. And Johnny is working on that. I don't know all of the details. It's apparently a bit broken at the moment, but some fixes were sent by our other contributors, and we are working on it. So what's in the Linux kernel fork? The first patches are just reverting the Itanium removal, right? If we want to bring Itanium back to the kernel after it was removed, you revert the commits which removed it. But that is not all, because the kernel, of course, changes. There are new changes added. Other code that was needed for Itanium to work is still being removed to this day. That is because of the complexity of the Linux kernel, right? You don't find all the code that you want to remove at once. You just find it in the future at some point and you remove it. So most of the other patches that we have in our patch set are reverts of features that were only needed for Itanium. For example, the support for the stack growing both up and down. That might be too technical, but Itanium has 2 stacks. One of the stack grows up, one of the stack grows down. So you need to support both of those. It's a small function in the kernel. And then you have updates of the Itanium architecture code to reflect the changes of the base kernel. For example, a kernel function adds an extra argument. We need to update the call to the kernel function in the Itanium code. Or the architecture-specific init code calls reshuffle what they call and what they do. And we need to update the Itanium code so that the machine is initialized in the proper order. And occasionally there were also fixes of upstream bugs affecting Itanium, and sometimes we found later that they also affected other architectures. There were also a few cleanups of Itanium code. Some of the Itanium-specific functions didn't used to have generic variants at the time Itanium support was added. So we just removed those and used the generic functions when the Itanium-specific ones stopped working. And sometimes we also add new features, for example, syscalls for Itanium, which is just adding some entries into the table. Yes, and so how much work does it take? Here I prepared some statistics. There are 97 extra commits in the latest release of the fork, which makes it roughly 9 commits per release. In total, we have about 300 additions and 800 deletions, which is just a few tens of additions and deletions per release. Of course, this does not capture the work that was actually done to write this code, but many of those are just moving code around. There is little new code, which makes sense because there are no more new Itanium machines that we would have to support in the kernel, right? If you have, for example, RISC-V or ARM or other architectures, each time a new CPU comes out or a new chipset comes out, this has to be implemented into the kernel, and those are huge additions to the code. But Itanium has been end of life, and all we have to do is to support the machines that already exist. And of course, this does not account all the work done debugging the issues. For example, in the latest kernel, some code was reshuffled and removed, so the kernel did not link properly, and it just crashed before it printed anything. So what I had to do was to capture the machine check exception data that was saved into the NVRAM of the server. And luckily, one of the things that were saved were the registers, and from the registers I could figure out where it was crashing, and eventually I could trace it back to the change in the linker script, which broke it. But I still think this is something doable by one dedicated hobbyist in their free time, unlike what the person who commented on the LWN article thought. But we do not have just one hobbyist. Many people joined me since I started this project. The main contributor has been Johnny, who has been running CI for every mainline and stable release. And he has been also compile testing and boot testing in the Ski emulator. The Ski emulator was created by HP to assist in the development of the Itanium architecture, but it has been abandoned and not working properly recently, and Johnny fixed it. And he also has much more machines than I have. I have just this one RX2620. He has about 10 different Itanium machines, and he's testing the kernel on all of them. You can look at this website in the slides. For every release, he prepares a table. The table says this release boots on this machine. It does not boot on this machine. And René Reber, who is the primary developer of T2 Linux, has also contributed. And recently, just before preparing this talk, there has been an interesting development. We got people from AOS COS Retro Linux, which is another source-based distribution that is trying to build a Linux distribution for retro machines. And they sent us pull requests fixing various errors in both kernel and glibc. So we now have about four to 5 people working at this in total, and we expect more interest as the HP Integrity machines become end of life. And the people from AOSC have already told me that in China, some government organizations were using those RX2800 i6 machines, and they are decommissioning them, and they will probably not be able to ship them out of China, but the machines are available. So we will see that in the next year. And here you can see Linux booting inside Ski in the CI pipeline. This is on GitHub. This is a metrics build from Johnny's Linux stable RC repository. It runs on x86 GitHub Actions machine. It starts the kernel in the Ski emulator. You can see here the emulated EFI and SAL firmware and the kernel build for this emulator, which is really good because you don't have to boot it on your machine The schemulator has some quirks. Sometimes it works even when it doesn't work on real hardware, and also the other way. Most importantly, it doesn't have a CPI, which is a very weird thing because all other Itanium machines besides Ski have a CPI, but it's a very good thing for testing. Yeah, so now about the distribution support. I hope I'm not going too fast. It sometimes happens to me. So as I said, we have T2 Linux. The latest ISO built by René is from October, from last month. And yes, the ISO ships with Wayland, if you have a graphics card that can support that. We also have Epic Slack, which is a version of Slackware that is maintained by Johnny, with some Itanium-specific patches, and AOSC, OS Retro are working on support, but it's not officially ready yet. Yeah, so this is a screenshot of Wayland running on Itanium. You can see this is an NVIDIA GeForce MX 4000 2003 PC card, so this is actually software rendering, but it works. But there have been some challenges that we faced as well, right? To do such kind of a silly project, it's never easy. And the biggest challenge, it might come as a surprising thing, but it was having to decide between a quick fix and a proper fix when rebasing on a new kernel release. This is a situation where there is a new kernel, you run git rebase, and it doesn't boot, and you found a patch and see, okay, this patch breaks it, but now what to do with it, right? And there are usually two things that you can do. One is reverting the upstream change, which is easy, but we wouldn't be able to integrate this upstream because they don't want their changes to be reverted if they also affect other architectures. And the other thing you can do is to adjust the Itanium-specific code so that it works with the upstream change, which is the proper way to do this, but it's more difficult. And because of this, I got stuck on several occasions, and there were multiple kernel releases where I just lost interest on this project. But Johnny created his own fork where he kept reverting everything aggressively, and he kept the kernel booting, and that managed to fix this issue. We had two people who each one of those people used a different approach, and that worked in the end. It seems a bit redundant, but it turned up well in the end. And the other challenge is toolchain support. GCC 15 was supposed to remove Itanium, but they eventually decided against it because René Rebe from T2 Linux, who works with us, stepped up as the maintainer. But we need contributions to fix bugs. The compiler evolves, and there are bugs that arise. And the other question, then, the challenge is what motivates us for keeping this historic architecture alive. And one motivation that Johnny likes a lot is that some bugs were first seen on Itanium in our CI, and then later they were reproduced on other architectures that are still in mainline. This has happened so far for Spark and also for M68K. But the main motivation for me is learning, community, and fun. It's exciting to boot a new kernel on a machine that is not officially supported anymore. And you can also reuse the commissioned hardware, of course. Itanium was a commercial failure, but there are still a lot of Itanium machines, and it would be a waste to make them unusable from the software side, especially when you consider the fact that those were high-quality business-oriented servers and workstations, and they aren't that likely to break that easily, unlike customer hardware. Consumer hardware that is sometimes, or at least it seems like that is designed to be planned to fail early. And the other interesting area is research of explicitly parallel computing. Itanium has a special way of statically scheduling instructions in the compiler, and sometimes it might work better. It has not proven this in practice, but you can try and optimize your own code on Itanium if you want to, and it might have some advantages. So this is an example of Brotli, which is a Google compression library that had a bug that was first seen on Itanium, and then it was also seen on Lungarch. And because of this bug, Brotli in 2025 actually included Itanium macros into the code. It's just a bit unexpected. But let's get back to the GCC thing. There are several bugs in the GCC Itanium backend, and because of this, I have involuntarily become a GCC developer. I have a master's degree from the Faculty of Informatics from Theory of Programming Languages, so it's not that big of a leap for me, but it was not something I would expect to be doing now. And we had two bugs. One of those was that zeroing registers on exiting a function, which is a security feature so that the register values are not leaked, crashes GCC if used on Itanium, and this is because Itanium has special predicate registers that are just 1 bit, and the implementation couldn't handle that. So I studied the GCC code. I wrote a custom Itanium specific handler for zeroing those registers, and I also worked with the people. in GCC that suggested how to do this for me, and I still have to send this patch and write tests for it and so on. So this is an issue I managed to fix. And there is another issue that is really Itanium specific, and that is with debugging for GCC emits different code than without debugging for which GCC folks treat as a bug. And it is because on Itanium, when you have instructions, you couple them into bundles by 3. You have 3 instructions in one bundle. And in the compiler, there is a finite state machine that creates those bundles, and it falls over on some debugging annotations, and it generates the instructions swapped. The semantics of the code is the same. All 3 instructions run in parallel, unless there's a barrier inside them. But GCC treats this as a bug, and GCC Bootstrap will fail in GCC 15 because of this, because it sees, okay, output with -G, the debug option is different than without -G, so it fails. So what are the next steps? We are getting to the end of the talk, and we would like to send an RFC back to the upstream Linux kernel, because clearly the concerns that Linus had were not quite funded, and we have people who can actually maintain this. And we have to keep in mind that the patch set has to be properly formatted with all of the kernel guidelines, like sign-offs, credits for the co-developed code, etc. And we have to also sort out all of the changes we made that might affect other architectures so that we don't break anything. But we expect that maintaining Itanium upstream will be easier, because people will stop deleting things that only affect Itanium, and we don't have to keep track of them and debug them and revert them, and we will also be notified of potential breaking changes. But of course, what we don't want to do is we don't want to put this burden on other developers. And we see that even now most breaking changes arrive into the RC1 release, and it's fine for us if we can fix them by the release. We don't need to be testing all of those RCs. There are not that many active Itanium machines that we run this on, so that would be fine by us. Yeah, so that's all from this presentation. Now I would like to show you another demo with a few benchmarks that I already shown you in the presentation, but it might be interesting to see them live. So I will switch back to the terminal. And there is a bug in my installation where I need to mount this PTS directory, otherwise I can't SSH into the machine, so I have to fix that. And now we should be able to SSH into the machine. Yeah, so this is the Itanium server. It has a genuine Intel 9040 dual-core CPU. And the cache values are wrong. Somehow Linux counts the hyperthreads twice, so it has 18 megabytes, not 36. But I have a folder here called llama.c. And you can see that I compiled this LLM implementation with a few compilers, with OCC, which is Open64, then with GCC, and also then with this BLAS library for the matrix vector multiplication. If you don't know Llama 2C, it's a simple education project by Andrej Karpathy that can do Llama model inference in under 1,000 lines of C code. And it's really good for testing this. And you can see that if I run this with the BLAS model, it will generate a story, and we get about 60 tokens per second. But if I run this just with plain GCC, it's much slower. All of those are parallelized. Those are using OpenMP, so it runs on both of the cores. Yeah, so this was the demo. And that's all from my talk. And if you have any questions, I would be happy to take them.
I have some questions. You mentioned the Itanium develop to be derivatives.
Yeah.
Did all the derivative commits apply to Unix, or how many of them failed?
The revert commits. Yeah. So the question is how many of the revert commits failed when reverting the Itanium removal. They tend to, I think we had about 3 failures. Most of them are merge conflicts on some lines. For example, in the documentation, there is a line that mentions 3 architectures, Itanium and 2 other architectures. And we have to resolve a merge conflict on that. And there was only one serious merge conflict in the code, which was something in the memory management subsystem that got fixed a long time ago, and that works. And other than that, this is not usually what fails. Usually what fails is because some other revert was added to the Linux kernel that breaks not the rebase of the patch set itself, but either the compilation or the boot itself. So has that answered your question?
Yes, thank you.
Okay.
I have a second question. You apparently tried to run some benchmarks. Have you tried to compare the results with other architectures that you have some graph tables?
I have not looked into this specific benchmark in this depth. I compared it to my other laptop, and I think I can run this benchmark even on this laptop if you want to see it. I think it's a bit more than. Yeah, I hope this is a good optimized version.
This particular benchmark is a bit random because if it generates different words for what it takes.
Yeah, there is a seed, and the seed is taken at random, but the inference speed does not vary by that much. It's pretty much constant. When I was testing this on another project, I used a static seed for it to be more precise, but since it doesn't matter that much, I didn't bother with it here. And I already had the numbers from before. I just looked them up. And on this machine, this is a non-parallelized version. It's running quite slowly. Maybe you can get a parallel one. Yeah, the performance highly depends on how you compile the program, of course. I need LM. Yeah, if the computer is running at I think 2 gigahertz, it's not running on the full 4 gigahertz, and I think if I optimize this correctly, it has something like 600 tokens per second. Okay, so the time is nearly up, so thank you for